Welcome to lesson 10. So, that is simultaneous sample and hold. Now, before we look at the AD converter, let us take a look at some sampling concepts. First thing that we must remember that the sampling value which you get from the AD converter is at the sampling instant. So, it is just at the sampling instant, and ideally speaking, so you have a signal. So, you have a signal analog and you are getting sampling it here and here and here. I am sort of exaggerating, actually you do not sample it so farther away, you sample it much closer, but just to drive home the point, what I am saying is that you have got the value of the signal here and the value of the signal here, and ideally speaking you do not know what the values of the signals are over let us say here or here or here, you do not know that because you have not got those values, right. So, what you do is you make an assumption, right. So, the hold why I say the hold strategy is that this hold is not the sample and hold, because the sample and hold will simply hold the signal, but when you are using the signals, for example, suppose you want to plot these signals on a graph. So, are you going to plot it as if this signal is held up to this point and then held up to this point and then comes down. So, are you going to plot it like this when you are going to plot it, or are you going to plot it like this? Then let me use a different color. The alternate way of plotting it would be to plot it from between this and this, it is a straight line like this, but between this and this you would say that I will interpolate, I will do a linear interpolation. So, when I will plot it, I will plot this yellow line, right. So, what I am saying is that if you want to plot it as a continuous signal, then you may choose appropriate interpolation strategies to construct a continuous signal which will be an approximate version of the old signal. Now, the question is, so obviously you can understand that how accurate this digital approximation is with the analog one depends on what. So, it depends on two things. Firstly, it depends on how close, like for example, if you had taken, rather than doing it this far, if you had divided it into let us say these intervals, and if you had got this value and this value and this value, then your approximation would have been like this, right. So, you would have gone from here to here, from here to here, and from here to here, and then here to, so you see that you are able to do, and then you would have got it here and here and here. So, you would have followed the analog signal much more close. So, in general closer sampling will give you better accuracy, but it is also a lot of, but it is also more work. So, more work, faster sampling and faster data processing. So, you have to determine what is the appropriate level of error that you can tolerate and what is the maximum amount of work that you can do within a given time, right. So, it turns out that there are certain fundamental principles to be obeyed, because if you do not do that, so ideally speaking you would like to sample at the lowest possible rate and trying to keep the error low, and especially you would like to keep the high frequency errors low. You may have some high frequency errors, but generally you want that the low frequency errors, that is let us say the average values over certain time intervals etc., should be pretty accurate, right. So, generally the low frequency component of the signal is actually of more use for the purposes that we are discussing, and so we do not want low frequency errors, right. So, that is what I am saying, that if you have an analog input and if you have 4 samples per cycle and if you have 8 samples per cycle and if you have 16 samples per cycle, so you see gradually you are getting a better and better representation of the analog input. Now, there is a benchmark rule which everybody talks about, is called the so called the Nyquist rate of sampling. Actually, this concept is explained in this diagram. that imagine that you actually truly have this sine wave which you are sampling. This is the real analog wave, right? This is the real analog wave, and being not aware of the Nyquist sampling theorem, you have sampled it at these points, right. So, what happens is that now you would like to reconstruct the signal, right. Now, in the computer you have got these values. So, when you reconstruct the signal, you will suppose you do a linear reconstruction. So, you will get this wave. So, you see that what you actually reconstructed is a much lower frequency sine wave, and this high frequency sine wave is completely lost. So, you made a major error here. It is not it turns out that theoretically speaking you cannot reconstruct a signal unless you sample it at twice the rate of the largest frequency content, that is largest frequency signal that is present. So, suppose you have a signal which is 5 hertz and another signal which is 100 hertz, then theoretically speaking you cannot reconstruct the signal even with an infinite number of samples unless you sample it at least at 200 hertz, right. But since we are not concerned with theoretical reconstruction, we have to actually reconstruct it. So, therefore, a practical rate would be 5 to 10 times of the maximum samples, maximum sampling maximum frequency signal present. So, if you have 100 hertz present, you typically like to sample it at 1 kilohertz or minimum 500 hertz, right. So, this says that, so basically if you do not do that, what there is something happens called aliasing. Aliasing means that one frequency signal will appear from the samples to be of completely a different frequency, it will appear as a different lower frequency signal. So, you are going to get a lot of low frequency error which is bad generally. So, exactly that is what is happening. So, your original signal was oops. So, your I do not know what is happening here, there is some problem with this, let me so yep, maybe now it will work now. Oh, I understand what is happening. Yep, but I do not understand how it came to be. Okay, so that is what is so that is what happens. One frequency appears in another frequency, and that is called aliasing. So, therefore, what do you do? What you do is, so now this leads to a concept. So, what you do is you actually need to restrict. So, you have a certain sampling rate which is fixed, you cannot change that, you do not know what frequency components are actually present in the analog signal. So, to make sure that you do not get low frequency errors, what you do is you actually put a filter whose cutoff frequency ensures that you have no frequencies beyond, let us say 1/10 of the sampling frequency. So, the sampling frequency is fixed, but the anti-aliasing, you actually put a filter which is called the anti-aliasing filter, which will ensure that whatever the signal content is, only those frequencies which are less than 1/10 of the sampling frequency are going to go through and appear at the input of the AD converter, the others are going to get blocked, so that they cannot create any low frequency error, right. Okay. Having understood the basic idea of sampling, we show so we say that an anti-aliasing filter is an analog filter that removes signal frequencies above fs by 2, where fs is the sample frequency. Actually, this fs by 2 is actually a theoretical rate. It will not remove above fs by 2, but would perhaps in a practical case remove frequencies above fs by 5 or even fs by 10. So, it is a low pass filter incidentally. So, this is So, you put that filter typically between the signal conditioner and the ADC, or in a multi-channel case you put it either at the channels or you put it after the multiplexer. So, here is a sample and hold circuit, very simple one. For example, so you can see that you have two amplifiers. This is nothing but a buffer. Okay. So, this is nothing but a buffer. So, whenever, so this is a switch, you know, this is an electronic switch. So, whenever you turn this switch on, this is a MOS. So, whenever you turn this switch on, what happens is that these 2 points you can say that they are connected. Okay. So, this is a buffer, unity gain buffer. So, whatever voltage you apply here, they will apply here and they will charge it up this capacitance very quickly. This switch resistance is small. So, it will fast charge up and this capacitor voltage will, as long as this switch is on, this capacitor voltage will follow this voltage, right. So, that is the sampling phase. So, as long as this switch is on, this voltage is tracking this voltage, changing along with that. The moment you turn this switch off, so now this switch is off and this capacitor voltage on this side sees high impedance, on this side also sees high impedance. So, the charge in the capacitor cannot escape, right. So, this voltage, the last voltage which the capacitor had is held and this is another buffer. So, this output will now be held at this voltage. Next time you put it on, again this capacitor voltage is going to change according to V1. So, you first switch it on, that is the sample command, this capacitor voltage starts tracking this voltage, then you switch it off and this voltage is held, which is transferred to the output, right. So, this is a typical sample and hold circuit. So, we have to understand that then there are a number of input analog channels and the input channels can be differential or single ended, as I said, and I explained the meaning. Now, this multiplexing says that if you are that is the maximum, suppose the AD converter can convert, let us say theoretically speaking 100,000 samples per second. If you are having 8 channels, then effectively each channel maximum can be sampled at 100,000 samples divided by 8. So, that is the throughput, and so the number of, so actually the oftentimes it happens that the sampling maximum sampling rate specifications of the AD converter are given and the number of channels are given. So, one has to be able to infer what is the maximum sampling frequency per channel. So, that is the final sampling frequency per channel that is going to be effective on the each channels. So, that is why this throughput question comes. So, next let's come to the question of quantization. So, we have now seen that an analog signal after sample and hold presents itself at the analog input pin of the AD converter, right. So, now it gets converted to an n bit digital number, right. So, for example, here is a case that suppose you have, this is a 3 bit ADC, right, that is somewhat hypothetical, but 3 bit ADC where, so which means, so with 3 bits you can represent 8 numbers 2 to the power 3, right, from 0, 1, 2, 3, 4 up to 2 to the power 3 minus 1, that is 7. So, 0 to 7. So, you see that the number 0 corresponds to 0 volts and the 1 corresponds to 0.125 volt. So, suppose every ADC has what is called an analog reference voltage which decides its dynamic range, as I was talking about. So, hypothetically if the dynamic range is 1 volt, generally it is 10 volts 10 volts is a very typical figure. Suppose it is 1 volt, then each, so 2 to the power 3 is equal to 1. So, 1 2 to the power 3 digital is equal to 1 volt. So, 1 digital or the number 001 represents 1 by 8 volts, right. So, this signal will become from 0 to from 0 0 0 to 0 0 1 when this signal reaches 0.125 volts or 1 by 8 volts. So, actually the any signal between 0 and 0.125 will get quantized to this 0, this is called quantization, right. Similarly, 0.125 to 0.25 all these will get mapped to 0.001 and so on, and finally 0.875 to 1 volts will get mapped to 111. So, this is quantization, and obviously the higher the number of bits, the smaller is the quantization interval and the better is the resolution. But then we can always make an AD converter of 32 bits, 64 bits, why not, because these are related to, because you have to make them, it is not just the number of bits, finally they must represent that mapping, that one represents 0.125, this must be accurate. So, when you increase the number of bits, you can understand that if you have, let us say, a 16 bit AD converter, then you have 1 by 65,000 is your resolution, right. So, the circuit should be able to resolve between 1 by 65,000 will be, you know, something like not even millivolts, right, it is of the order of microvolts. So, the circuit should be so accurate that, and the environment should be so less noisy that you will be able to separate between those. If you do not do that, then your AD converter, just because of noise, it will this, even if you present a constant signal, its digital bits will start oscillating, and the last few bits will anyway be useless because of noise. So, that is why it is very difficult to construct AD converters of number of bits more than 18 maybe, and generally for this kind of things 12 to 16 are used, 12, 14 or 16. So, we have, so you see AD converter resolution and range. So, now finally the signal, the accuracy is affected by the range. So, range is, so finally when you have a number, how do you convert that number? Suppose you have a number 001 and it is a 3 bit AD converter. So, the number is actually 001 divided by 2 to the power 3. So, 001 by 2 to the power 3, which is, so it is 1 by 8 into the reference voltage, in this case suppose it is 1 volt. So, it is 0.125 volts. So, that is how, so obviously you can understand that as the number of bits will go up, the resolution will increase, and the minimum, on the other hand, if you have a, suppose you have a 10 volts range and you have a 1 volt signal. Now, the point is that you could actually amplify this 1 volt signal. So, if you use a, let us say we can write here also that suppose you have a converter which is a dynamic range of 10 volts and you are giving it a signal whose peak to peak value is 1 volt, right. So, then peak to peak value is 1 volt means the lowest number, and it is a 3 bit converter. So, then the lowest value is 1.25. So, this 0 to 1 minus 1 to or let us say 0 to, let us talk about unipolar signals, no, not negative. So, suppose 0 to 1, if you have a signal, then always you will get the value 0, it will the variation will not be caught at all. On the other hand, if you had amplified it this 1 volt to 10 volt and then taken care of this amplification factor in your software, then this signal, this 1 volt signal variation would have been captured up to 3 bit resolution. So, this shows that always it is, you must have amplification, enough amplification, that is why people sometimes put programmable gain amplifiers, amplifiers whose gains can be changed again under software controls, but although they are expensive. So, you need to always amplify the signal, so that the AD converter dynamic range, that is the range between the reference voltage up to the reference voltage, is actually effectively utilized by the input, then you get the best resolution for a given number of bits. This is important to remember during data acquisition. So, now we are going to take a look at some AD converters, but then before that we have a, we take a look at a DA converter, because an AD converter circuit, that is the most, one of the most common things like the successive approximation converter uses a DA converter. So, we just take a quick look at what is a digital to analog converter, that is, if we put a set of digital bits, how can we get an analog voltage which will be proportional to that number. So, this is called an R2R ladder network for obvious reasons. You can see that 2R, 2R. So, there are some R and there are some 2R resistances, they are in double ratio. So, that is why this is called an R to R ladder network, ladder because of this form structure. So, you see that you can, it is rather easy to show using simple network theory, that you see these are the switches which are actually controlled by these bits. So, now suppose let us take the simplest case, that if I switch only this MSB. So, it will get connected here and all the others are connected to this ground, you see this is connected to ground. So, then what is the voltage that will appear here? That is very simple, because you have 2R and 2R in parallel now, this is connected to ground. So, therefore, this resistance is R. Now, that R and this R is in series. So, it is 2R, again 2R and 2R in parallel, again R and R in series, again 2R and so on. So, finally, what you get is finally you get this network. So, you have a 2R, you have an 2R and then you have a voltage source. So, this is your Vref, and then you have an R and then you have an amplifier, and here you have a 2R. So, R, 2R, 2R, 2R. So, if you do a Thevenin's circuit for this what will be this voltage? This voltage is, so the open circuit voltage is going to be V by 2. So, it is going to be V by 2 here, and what is going to be the Thevenin impedance? It is going to be 2R parallel 2R, which is R. So, this circuit can be further reduced into a network of this form. So, it can be further reduced as V by 2 in series with a resistance R, which is a Thevenin network, then another R, which is this one, and then the amplifier, which is 2R. So, this R and this R will make 2R, and this 2R and 2R will give you a gain of 1. So, you get V by 2, right. And so, if you have a total range of the AD converters, then the MSB should have a total range of n bit converter, then the MSB should have a weightage of V by 2, and you can see that if you only switch on this MSB, you get a Vref by 2 signal here. In this way, you can show that if you kept all the others grounded and you put on the next bit on, you would have got V by 4, similarly V by 8 and so on. So, now if you, depending on your digital numbers, if you switch on some of them and do not switch on some of them, then you get a corresponding, because this is a linear circuit. So, you are going to get superposition principle. So, the final signal is going to be Vref properly weighted with the binary number weighting. So, you will get a analog voltage which is going to be proportional to the digital number. That is why it is called a digital to analog converter. So, in our so, for example, in this AD converter, which is called successive approximation converter, principle is very simple. You put a signal, the signal first compares whether, suppose this is initially this is 0, initially this is 0, right. So, this just compares whether this should be, this is higher or this is higher. So, if this is higher, it puts it 1. Now, when it puts it 1, it sets the, this is some logic. So, this will put the maximum bit high, that will no. So, maximum bit means V by 2. So, that will come through the DA converter and will apply a V by 2 here. Now, the question is whether this analog signal is greater than V by 2 or less than V by 2. If it is greater than V by 2, then it is still 1, then the next bit will be put. So, in this way, first the MSB is put, then the next bit put, till this signal crosses this signal, and then at that level it is stopped. So, that is how you just compare it with a number of digital numbers till it exceeds, and at that point you stop. So, you get, so when you stop, you get a set of digital bits which is closest to this analog signal, right. So, this is how you convert, this is how a typical successive approximation converter is, and just one way. There are many various other converters. For example, a very fast converter is called flash ADC. We are not going to discuss that because we do not have enough time, but this is a converter where there you do it bit by bit. So, you need at least, worst case you can need n times you can go through this cycle of setting and resetting bits. So, you need more time. On the other hand, in this converter the whole conversion is just in 1 clock cycle. So, it is much faster, but then it requires a huge resistance network and they have to be very precise, otherwise you are going to get errors. So, this is a converter which is, therefore, this converter has some problems, and although it is very fast. So, we are not going to look at that too much. If you compare, there are various kinds of converters, and we are, for example, there are other converters too. We are talking about flash, we saw successive approximation. There are some converters which are called voltage to frequency or integrating converters, which are very slow but very accurate. So, you can have typical idea about the number of bits. Flash is 4 to 8 bits, typically less number of bits, but very fast conversion. So, you can go up to 500 megahertz kind of conversions. Then successive approximation is very widely used, 8 to 16 bits possible generally, and medium sampling rates. For most processes, successive approximation is good enough. And then you have integrating converters which are quite slow but very accurate, because they do an input averaging over a long time, and therefore they have good response to noise. So, having seen that, so now we have seen eddy conversion. Now we come to the system level discussion, that typically there are two kinds of data acquisition systems that you find. One are called external bus or remote. So, there what happens is that the computer is in a separate place generally, and oops, I do not know what is happening. Yep. So, you see here these are all the signals, analog signals are getting terminated. Let us assume that it is signal conditioned, we are not, if it is not that, then it will be conditioned. Then the eddy conversion, we have seen what is eddy conversion. Then now what happens is that this thing, this physical, these systems, boxes are separate, are situated at a separate place. They have their own separate power supplies. They are situated possibly much closer to the field, and then here so after eddy conversion, and they have their own processors. So, the value is firstly coming to that embedded communication controller processor, and then using some very standard communication protocol, either RS-232, 422, 485 or IEEE 488. There are number of protocols by which through computer communication it is coming to what is known as the host computer, where this data is going to be used. So, this is a small box which is going to be close to the process, and then one wire is going to come, generally serial communication coming to the computer. So, this is an external bus remote data acquisition system. The advantages are that they can connect to any host computer, so it is so close to the field, right. Disadvantage is that generally data acquisition rates are limited because of this serial communication. So, you get slightly slower rates of communication, but if that is good enough for you, it is okay. Second kinds of things are internal PC bus data acquisition systems, where the data acquisition system sits right inside the PC box, right. So, and then they will communicate with the PC through the PCI bus, which is much higher speed and which is parallel interfacing, right. So, the data acquisition rates can go much faster, but this means that the PC has to go close to the field, otherwise you are going to have long cablings to the PC, right. So, similarly these are generally designed for specific machines like Windows PCs. So, this is a typical picture of a PC data acquisition board. So, what happens is that the board itself has a CPU which transfers the data, because it sits on the PC bus. So, it will transfer the data to the PC memory, and then the PC CPU can actually take it from the memory and then do a display, right. So, they are generally designed for these kind of Windows kind of PCs, and they are very common and they are rather cheap, and especially can be used in a very much in a laboratory scenario and widely used. So, these are the basic two types of data acquisition systems. If you take a typical specification of a data acquisition system, they will mention things like power consumption. See, 5 volt supply has a lot of current requirement because of the digital circuits, then a 12 volt supply for analog, The number of channels is very important. Typically you have about 8 analog channels, either single ended, you can have 8 single ended, 8 differential or 16 single ended channels. Typically number of digital channels are much more, 64 like that, because they take only one signal each. Resolution says how many bit converter is being used, so it is a 12 bit converter. Accuracy, the AD converter type, then this full scale, this is the dynamic range. So, it is saying that the dynamic range is 0 to 10 volt DC. Then the AD converter codes can be available in various formats, whether it is 2's complement, true binary, offset binary, various kinds of digital codes are there. These two specification, gain and zero drift specifications, are for the signal conditioning block which is there in this thing. So, if they will have an amplifier, and that amplifier gain variation and zero drift can be specified. And finally, the acquisition time, which says that the acquisition time is of the order of 4 microseconds. So these are typical specifications of a data acquisition system which you need to look at when you select one. So, similarly, finally is data acquisition software. I do not want to talk much about it. Only thing is that sometimes you can either go for this data acquisition software will only come up with some certain drivers, and then you can write your own C or basic programs to use the data acquisition systems, but that requires a lot of programming, although it can give you a lot of flexibility in the sense that you can do anything you want with the data, the raw data is made available, but this requires a lot of programming, and often in an industrial situation it is not preferred. So, people use data acquisition software packages. So, in programmable software the advantage is flexibility and the disadvantage is complexity and a very steep learning curve. While if you have data acquisition software, then it does not require programming. Generally it requires graphical programming, in the sense that using very common sense and domain related quantities you can actually configure the system and get data and then display it. So, enables developers to design custom instruments best suited to their application. There are various examples. For example, a common one with which I am familiar is LabVIEW, but there are few others also. So, what we have done during this course, this lesson, we have seen the architecture of data acquisition systems, we have seen the sampling concepts, we have seen some details of analog to digital conversion, and finally we have taken a look at some data acquisition hardware and software features. So, points to ponder is mention 3 ways in which signal conditioning affects conversion accuracy. So, I have already talked about dynamic range, you can think of some others. State where simultaneous sampling and hold is necessary and where it is not. So, as I said, it is related to the frequency content of the signals and the speed of conversion of your AD converter and the number of channels, of course. What happens if an anti-aliasing filter is not used before an ADC? So, you have to go through, if the ADC is successive approximation or if the ADC is flash. So, choose the ADC and then go through it and see that suppose in the middle, suppose the signal just goes to 0, then what will happen? Sometimes it may give you wrong results, sometimes it may not. Name 3 typical functions of a data acquisition software. So, one of them could be display. You can figure out the other 2 by looking at some of these software which are advertised on the internet. So, that is all for today. Thank you very much.